Our first definition inside this chapter is parallel lines. Okay, and this is one of those really bad vocabulary words that when you were younger, you were given a bad definition for. Okay, when you were younger, what did they tell you parallel lines were? Lines that never touch, lines that do not intersect, and that is a key component. But when we write it that way, what we do is we actually include an infinite number of scenarios in which we classify things incorrectly. We classify a grouping of lines that do not touch, but do not have the other kind of conditional relationships that parallel lines end up having. Okay? So we need to make sure that we eliminate those infinite number of examples of lines that do not touch, but are not parallel. Okay? Because they don't have any of the other relationships that parallel have. So the way we fix it is we add that word right there. We add coplanar. And the reason we do this, guys, is because when you were younger, your brain structure is not ready for being able to understand what coplanar means. When you're, I don't know when you first learned parallel, maybe third or fourth grade, right? Your brain structure is not ready to understand what planes are. Still might not be ready to understand what planes are at this level, okay? And the idea of what coplanar refers to. Some shorthand terminology or shorthand symbols that we use those two little vertical bars to mean parallel, okay? Or is parallel to. They're all mathematics. If you just Googled like mathematics symbols, okay, you get a kind of probably a PDF somewhere of what seems to be an endless list of symbols that we use to represent phrases. That's one for parallel. There's one for perpendicular as well. Other classes said they've seen that before. Okay, you guys agree with that? You've dealt with. And the way I read this is AE is line AE is parallel to line BF. You've seen that before? Okay. As we kind of work through these definitions, I want to at the same time give you kind of visuals of this stuff with GeoGebra and explain to you how you're going to see it in your homework. So give me a moment to set this up. All right, so would you guys agree that this three-dimensional shape has some segments or lines that are created? Okay, so one of the questions that you can get in your homework, this happens a lot, is that they're going to ask you, are maybe this segment here and that segment there, are they parallel? Yeah. Okay, the argument to that is yes, they do not touch. Okay. And they'll, in the directions, they'll say if they look parallel, then assume that they are parallel. Okay? So these look like they're not going to touch as I extend the lines, right? That kind of makes sense. That's what they mean by that. But those two lines will not intersect as far as we kind of look at them. Does that make sense? Okay. Now here's what we need to understand is that those segments are parallel because the lines that they came from were parallel. Does that make sense to everybody? So when you want to ask, are rays parallel, are segments parallel, we need to answer that question in regards to were the lines that they came from parallel. Okay? So those are parallel. And another reason, obviously, is because they don't touch. The second component to the definition was that they had to be in the same plane. Would you agree that those black lines are in that blue plane? Okay, so they're coplanar. If I look at, let's say, that line there and this one back there. Okay, do they touch? No, but are they parallel? Okay, they are. Now, even though the plane that you can't, or that is containing both of them, both those lines, is not drawn up there, it's not highlighted, but we need 3 points to determine a plane, right? Can I put that plane in there? Can you see that both those black lines would be contained or drawn in that blue plane? That kind of makes sense to everybody? So even though the plane, and that's the thing that people struggle with that question there, even though that plane is not highlighted initially for us, we can insert one in there because we know all we need is 3 points. Okay? Okay? So those would be considered parallel. But here's my question. What about those two? Are they parallel? Okay, so the answer to that is no, but why? Huh? They're not coplanar. Okay? So that, there's a couple different planes that we can look at here. Would you guys agree that this black line is the intersection of that top plane and that plane right there? So we can look at either one of those planes and say that that black line is contained within it. Or we can even go back and look at that diagonal plane that we had drawn in here or whatever. But that plane, let's just draw one of those. Let's say that we put that plane in there. Okay? So that black line is in that blue plane. Let's look at this blue line. Would you guys agree that the blue line, oh, let me click the plane tool. The blue line is in that plane? That makes sense? Are they the same plane? No. Okay. We could have also, like I said, looked at maybe the blue line being inside that orange plane. Okay. Still not the same as the blue plane, right? Okay. So those two lines are not parallel, even though they do not intersect. Now, the reason for this, the reason we don't consider those things parallel is because these two lines, guys, do not have the same relationship, okay, or the series of relationships that we're going to talk about that maybe these two lines have. Does that make sense to everybody? Okay. There's going to be a series of statements that we talk about throughout this course about those two lines right there. Those are parallel because they're in the same plane, right? They have a series of relationships that the other lines that we're going to identify here in a moment do not necessarily have. Anybody know what we refer to these other lines as? We said it earlier this week, or not this week, earlier this year, maybe when we first started talking about conditional statements. This was an example in one of our homework questions. I heard it. Started with S, skew. Okay? So those two lines are referred to as skew lines. The way I remember what a skew line is, let me get rid of some of this stuff. Let me get rid of the prism. Okay? So look at the blue line and the black line. They are said to be skew. Let's think about that plane, that orange plane, as being like a piece of meat, a steak. Okay? If I have a metal rod that I push through that steak like this way, we call that metal rod a skewer. Okay? Now, that's the way I remember it, and what that means then to me is that any blue line then, like this blue one, so the infinite number of blue lines that are like it, would then be skewed to the black one. Does that make sense? Okay. We go to, I think I got a picture in the PowerPoint. Okay. So that black line is my skewer, right? If you were to take a Sharpie and draw any line that you wanted to on that stake, it would be skewed with that black one, as long as it did not go through the point up there that the black one's going through the plane on. Does that make sense? So as long as you do not... All right, so take a Sharpie marker, draw any line on this stake that you want to, as long as it doesn't go through that point right there. The black line and the one you draw would be skewed to one another. Okay? All right, that's just how I've always remembered what skew meant, and maybe you can see the logic then of why we call it a skewer. Here are some alternative definitions that we use to talk about parallel lines. Okay? And you're going to hear me say the word parallelism because we can use the same thing to talk about planes sometimes, at least that second bullet where it says parallel lines or two lines, which the distance between two lines is always constant. That's kind of how we'll talk about the definition of parallel planes eventually. The parallel lines, you guys learned in Algebra 1. Parallel lines have the same slope, right? Look at these two lines right here, and I'll go back to this so you write that down. But these are the two lines that I have drawn. The algebra is over here on the left. What do you notice about the x coefficient? It's the same. All right. When the lines are not parallel, what do you recognize about the x coefficients? They're different, right? That means the lines will intersect. So in a rise and a run, okay, the vertical change and the horizontal change are the same for two lines. That means they're never going to cross each other. Okay. A byproduct of that basically forces those two lines to have a distance between them that never changes. A distance between them that is constant. Okay? So that's another way we talk about parallelism for lines, is that the distance between the two lines is never changing, or a word for never changing is constant, right? Excuse me. We don't have the time to, I don't think, at least right now, to kind of talk about how I developed this distance right here. Okay? Would you guys agree that that 3.13, as I move that between those two lines, is never changing? So because it's never changing, it's constant. If the lines were not parallel, just change it just a little bit. What's happening now to that distance? It's changing, right? And eventually that distance will get to 0. Can you visualize where they would be when it gets to 0? It would be the point of intersection. It basically says that those 2 points that were defining that segment now are 1 point. Okay? But if the lines are parallel, that distance is the same. Is that kind of like the rails on a railroad track? Okay, or the rails on a ladder. Maybe this is the rung of a ladder where you put your feet in your hands. They should always be the same on a ladder, right? Okay, for the most part. There are some ladders that look like A's, right? Huh? Okay, they are scary. All right, so planes are parallel as well, guys. I'm not going to get into that too deep with you because we've got some vocabulary here to talk about. But if I were to look back at this picture here, would you guys agree that that plane, come on, did this last period. Well, we'll do it this way. That one and that one, would you guys agree that those darker planes are parallel? It's because they do not touch each other, right? They do not cross. Okay. What about that one and that one? Are they parallel? No, because when we talk about plane, we got to talk about them moving on forever, right? So I look at that one going on forever, and this one going on forever. You do see it, they eventually do cross, right? Okay, so those are some questions that you might be asked in your homework about parallel lines, parallel planes, that kind of stuff. All right, so that gets us to kind of the thing that I really want to talk about. We've got 10 minutes. We should be able to get through these vocabulary words pretty quickly, but it'll probably be like 314, 315, so just stay with me. If you don't get them all written down, you can always go back to the PowerPoint under 3.1 and write these down. But a transversal is a line that intersects two other lines at different points. Okay? A transversal is some line that intersects two other lines at different points. The reason they have to use the word different point, we've seen this once before, but all it does is it guarantees that these two lines L and M, that's line L, line M. This line here is our transversal, but the phrase different or distinct point just guarantees that line L and M are different lines. If I just said intersects two lines, then L and M could be the same line. We want these two lines to be coplanar. A lot of the relationships that we see here would not exist if we were looking at the lines being non-coplanar, the lines being skewed to one another. So line T is a transversal in this picture. Okay, L and M are not transversals. L and M are just your general normal lines. Okay, we don't have a special name for them. But when we do this, when we have line L and M, okay, can you see the region that is kind of sandwiched between L and M? That region there? That region we're going to refer to as the interior. It's the inside of lines L and M. Okay? Well, if that's the interior, everything else must be the exterior. Okay? So what we like to do, every time that I create, and you can draw this picture and convince yourself of this, but no matter how I draw two lines cut by a transversal, you're always going to create 4 angles there, 4 angles there, right? So you get 8 total angles. We want to talk about those angles, and that's kind of what this first couple of sections in this chapter are about, are identifying and talking about those angles. So here we got 8 angles. We want to talk about them, so we need, and grouping them up into essentially groups of 2. They're going to have special relationships tomorrow. So this kind of says these definitions set up those relationships eventually tomorrow. But we want to talk about angles 4, 3, 5, and 6 as a group of 4, and then we'll dwindle that down to a group of 2. But 4, 3, 5, and 6, you agree that they're interior angles? Because they're between our lines L and M, right? 1, 2, 8, and 7, they are exterior angles because they're on the outside of lines L and M. Okay? So our 8 angles are going to have those 2 adjectives, either interior or exterior. The next thing we're going to do is we're going to look at whether the angles are on the same side or on different sides of the transversal. Okay? So this word here, alternate means back and forth, right? I have alternating current. It goes back and forth in electricity. Okay? So alternate means back and forth, and that's in regards to the transversal. So alternate sides are back and forth across the transversal. And interior tells me it has to be between the 2 lines. Does that make sense? I like to look at the interior portion first, so it's going to make me focus on 4, 3, 5, and 6. Those are the interior angles. Alternate, then, is defined by the non-adjacent angles that are on opposite sides of the transversal. Non-adjacent. When they say non-adjacent, that eliminates being able to look at 4 and 3 and 5 and 6 as a group. Does that make sense? Because 4 and 3 are adjacent, correct? 5 and 6 are adjacent. So that means 4 and 6 have to be the ones that are non-adjacent. 3 and 5 have to be non-adjacent. So as a group, angle 4 and angle 6, by definition, we say those are alternate interior angles. They're alternate because one's on one side of the transversal, the other one's on the alternate side or the opposite side, right? They're interior because they're on the inside of L and M. Okay? 3 and 5 are another group. Okay? You're going to find out the benefit of knowing those locations tomorrow. We're going to do something with these lines L and M tomorrow. that develops a really nice relationship here. What would you say that angle 2, just based off this definition, how we structured it, what would you say angle 2 and angle 8 would be called? Alternate exterior. So that's the next definition. Alternate exterior, non-adjacent exterior angles. Okay? Because 1 and 2 could still be exterior, right? Okay, they'd be alternate, but we don't want them to be adjacent. So I don't want to talk about 1 and 2. I want to talk about 2 and 8. I want to talk about 1 and 7. Okay? Those are referred to as alternate exterior angles. Alternate exterior angles. Tomorrow, we'll have some, like I said, we'll have some nice relationships about angle 1 and angle 7. We'll have a nice relationship about 2 and 8. We already, no matter what we have, before we even get tomorrow, we already know a relationship between 1 and 2, right? 1 and 2 are going to be supplementary, correct? So there's really no need right now to talk about they're a linear pair. We've already got a way of identifying them and talking about them. So now we're trying to identify and talk about other things. Okay? So 1 and 7, alternate exterior. Okay? Now, based off of what we've learned so far, what do you think is a name for angles 3 and 6 based on their location in one another? Are they alternate? Are they on different sides? So if they're not on different sides, what's a phrase that you could use? If they're not on different sides of the transversal, they have to be on the same side. And where are they in regards to L and M? Are they on the exterior or are they on the interior? Interior. So what would you call 3 and 6? Come on, you just did it. Piece together. Same side interior. Okay. Same side interior angles are angles that are on the same side of the transversal and they're interior. So 3 and 6 are one grouping, 4 and 5 are another grouping. Okay. Every one of these are going to be 4 total, but these first 3, alternate interior, alternate exterior, same side, there's always 2 groupings. Okay, so 3 and 6 are one grouping, 4 and 5 are the other grouping for same side interior. Okay? All right, now the next definition kind of stinks. Terrible. Okay? Let me show it for you. Why does this definition stink? What's the problem with it? What have we said? Absolutely. Okay, if I don't know what corresponding means, then I can't address this definition, right? Corresponding means kind of a matching position or matching time. Guys, that kind of makes sense? What room in the building corresponds to this room when it's on the first floor? Huh? We're one right underneath us. Whose room is that? What is that? It's the office, right? Half of it's going to be the copying machines are over here. Mr. Jesco's office is like right over here. Does that make sense? Okay? Or actually over there, and then you got part of the other office here. But if I look at Mrs. Oliver's room, who's going to correspond to that on the first floor? This is you, right? Okay. What about Mr. Gomez's room? Who's going to be right underneath him? Mr. Steidel, right? So those are corresponding rooms on floors, correct? Does everyone understand that idea? Okay. So if I look at my lines L and M here as kind of floors in a building, do you guys see that angle 2 would correspond to angle 6? Does that kind of make sense? Angle 2 and angle 6. Angle 2 is like your second story classroom. Angle 6 is your first story classroom. And if you could do that with 2 and 6, then every other grouping of angles can be addressed kind of the same way. 1 goes with 5. 4 goes with 8. 3 goes with 7. And here we actually have 4 groupings of what we call corresponding angles. All right? The way I like to visualize it, and my computer's freezing, kind of. I'm not going to be able to show you. Maybe I'll show you tomorrow. Is that I like to take that line L and slide line L down, and you can change its slope so it matches up to M. Can you see that 2 would land on top of 6, 3 would land on top of 7, 4 on 8, and 1 on 5? Does that make sense? Okay. So allow yourself to kind of slide line L down on M, or M on top of L, Doesn't matter which order you go, but you can see then the parts that would correspond or the parts that would match up. All right? Make sure that you understand those vocabulary words tomorrow when we get here, because we're going to build on them. We're going to develop relationships tomorrow with them. Have a great evening. Don't forget to do your take-home test.